The suspense is killing me. Okay, happy November. Backyard Naturalist. It's Friday morning at 9 and some change here in Milwaukee, which means it's time for another installment of Backyard Naturalist. It's Central Daylight Time, and this might be one of the last times we ever can say that it's Central Daylight Time. If the measure passes Congress, this Sunday might be the last time we ever have to change clocks between daylight and standard times, which I don't know how you feel about that, but it makes me happy. What it means is that next week it's going to get dark earlier, and it's like ripping the Band-Aid. It's a boom hour. It also means it gets light earlier, and it means you get an extra hour to do whatever you want. If we switch to permanent standard times, then it means slightly earlier sunsets in the summer here in Milwaukee. So, getting dark at 10 o'clock is going to be replaced by getting dark at 9 o'clock at night. But scientists suggest, and the research suggests, that this switch is better for society, is better for our sleep cycles, especially if you have small kids. It means fewer accidents and so forth. It also means that the winter dark nights are going to come upon us more gradually than so kind of in our face like it will next weekend. And one of the things that I personally enjoy living in the North is embracing the darkness. I learned that from Baldur Gylfa, a phenomenal guide that led the UEC Eco Travel trip to Iceland. But if you live in Iceland and it's pretty dark there half the year, embracing the darkness is kind of a survival strategy. And it can also be a beautiful thing. And I know seasonal disorder can be very real, and I don't want to minimize that, but if you can channel your inner vampire, start to embrace darkness a bit more, it can be fun, it can be cathartic. It allows you to embrace that hygge, reading a good book with a hot cider and a blanket next to a lamp when it's dark. But anyway, today we're returning to the second set of stories surrounding water, an element for which it is impossible to overstate its importance to life, in episode 10 of season 4 of the Backyard Naturalist, Do the Right Thing. It is also impossible to overstate my gratitude for you all just for being here today with us. And I'm sending a little extra gratitude to members of the Urban Ecology Center and those of you that have subscribed to the Backyard Naturalist. In fact, I personally think that with gift giving seasons coming up, a gift subscription to the Backyard Naturalist would be a especially good gift for somebody that's hard to figure out in terms of giving a good gift. Also, another very quick reminder that we will be exploring Cudahy Woods tomorrow in person. You can still sign up. We'll be doing this in front, not in front of a screen, 1 o'clock tomorrow, hopefully weather dependent. If you register, we'll talk about it then. And this is an amazing example of old growth in Milwaukee. It's a place, if you haven't seen it, you really should see it. It's not very big, but as a colleague of mine recently mentioned, it's a great place to see really big trees in Milwaukee. It's open to everyone. It's free to subscribers as a token of our gratitude that you're able to and choose to support this community and this program. And the itinerary is almost set. Most of the T's are dotted and the I's are crossed. At least my I's are crossed. We'll be traveling to Indiana and Michigan, November 30th through December 2nd, to visit a truly unique and breathtaking landscape, the Indiana Dunes, and Jasper Pulaski Fish and Wildlife Area, which is one of the biggest staging areas of migrating sandhill crane, where we could easily see more than 10,000 cranes in a single field. It's a truly unique, immersive experience. And if you've been joining us regularly, you've noticed my renewed interest in paying attention to astronomical events over the past months, particularly the human desire to understand these upper extensions of our backyards and green spaces. It's been fun to stay abreast of this. So I'll start with an update on the Hakuto R mission, which, if successful, will be the first private moon mission in human history. It's scheduled for launch November 9th. An Israeli company attempted to do something similar in 2019, but the lander crashed on the surface, so it wasn't successful. The Hokuto R is really interesting. It's being developed as kind of the first payload delivery system to the moon, which is crazy to think about, but makes sense, right? If there's a lot of interest in getting back on the moon. A lot of countries, a lot of private companies are doing a lot to get us back on the moon, and not just on the moon, like on the moon. So with that, it's not going to be long before we're there for an extended stay, and just like on a space station, and they're probably the folks that are up there are going to need stuff. Or if you're building a structure, you're going to want to send the lumber ahead of time. So it's a private Japanese run commercial mission. It's actually a joint venture between Japan and the United Arab Emirates, and there's a few other countries involved, Canada, the United States, but this mission is starting to look at the feasibility of a lunar payload delivery system, getting stuff to the moon. It's kind of like an Amazon service to the moon. The future's here, man. It's on this mission, they're carrying 2 rovers. One is like a baseball-sized 2-wheeled transforming robot. So in my mind, it's a cross between BD-8 and Bumblebee. It's also carrying a more standard Canadian 4-wheel rover. That's also Japanese. It's carrying a Canadian lunar camera, and then an Emirati from the United Emirates artificial intelligence flight computer. So we're getting artificial intelligence on the moon. Good or scary, I don't know. The goal is to start getting lots of rovers and things exploring the surface of the moon before the humans get there. So our humans will be welcomed by this community of robots and rovers that will have been there to lay the groundwork. Hopefully they're still on our side, on humanity's side. Fascinating and scary. And then, so in a short while, the lunar surface is going to be buzzing with activity, and there's going to be coinciding activity in the lunar skies. So in less than 2 weeks, NASA's Capstone mission will enter the moon's orbit, and that's really studying, the Hokuto is studying the feasibility of things on the land. This will be studying the feasibility of keeping things in orbit around the moon. There will eventually be a lunar version of the space station that's currently around Earth. There'll be one of those around the moon. That'll be, it'll be occupied by people. And so we'll have a space station on the Earth, a space station on the moon, both likely with permanent human presence. And then the Capstone is also supporting the other thing we've been following for quite a while, the Artemis, which is, so many setbacks, but fingers crossed, November 14th launch date, precursor to Artemis 2, which will put humans into lunar orbit, and Artemis 3, which will land humans on the moon. With all of this happening, it's quite possible, this is a realistic possibility, that by the end of this decade, there will be a permanent human presence on and around the moon, like people and satellites in orbit, people stationed on the moon with all those rovers and robots. And this isn't a future that we have to wait for our grandkids to see. It's quite possible that we'll all get to witness this lunacy. We'll see, and we'll continue to follow it here. One astronomical spectacle that will be happening regardless of human exploration will be the Leonid meteor shower. You can actually start to see meteors from the shower already, but it'll reach the peak the evening and early morning of November 17th and 18th. This is a shower that has produced in the past meteor storms where you have rates exceeding 1,000 fireballs an hour. This year, the forecast, you're only going to see about 15 meteors per hour, so much, much, much less, because we're not really scheduled to enter or forecast to enter any debris fields. This is going through the parent comet Tempel-Tuttle's tail, and it's not really until the year 2099 that we'll get one of those big storms again. So that is the case that, yeah, it'll be our grandkids or grandpuppies that will be witnessing that. And then finally, if you're good at staying up late, or actually probably waking up early, which is going to be easier to do after next weekend, if the skies are clear, you could be treated to a total lunar eclipse. the morning of November 7th. That's coming up soon. So total eclipse begins at 4:16 a.m. and ends at 5:41 a.m. Maximum is just before 5 a.m. But if you think about daylight savings, that's really like 6 a.m. now. So this might be an easy one to get up for. And I'll probably get up and look for it. Okay, if the skies are clear. Okay, water part 2. In part 1, we kind of talked about a few key points about water. Essentially, that water is a very strangely behaving liquid. It does not behave like most liquids, and that's really good. It's really important for life. We talked about how a water molecule itself is 2 hydrogens and an oxygen that are held together by a strong covalent bond in which the hydrogen and oxygen atoms share electrons. Very strong bond. And then because the oxygen side does a better job of like keeping the electrons close, the oxygen side retains a negative charge, and then the hydrogen sides retain a positive charge. This charge, this covalently produced charge, allows water molecules themselves to also be attracted to each other. So hydrogen is attracted to oxygen very strongly, but then water molecules themselves are attracted to each other because they each have a positive and negative charge. They like being around other water molecules. This allows for surface tension, which is extremely important to life in many ways. And pretty much it's that hydrogen bond between water molecules that gives water these really important and unique properties in so many ways. It's a strong bond, but it's movable and flexible. And this charged attraction between water molecules also makes water a really good solvent. So in a glass of water, think about this before you drink it, there's acid and base in there. There's freely moving hydrogen ions, positive and negative charges. That makes it good at surrounding and dissolving other things that also are charged, like sodium and chloride. So water is excellent at dissolving minerals, ions, salts, but thankfully, it dissolves a lot, but it does not dissolve fatty lipids, which allows our cells to keep water in. Otherwise, the water would just dissolve us, and we'd be this massive oozy creature. So it allows us to keep water in. It also allows us ions and information to travel in and out of cells along neurons, which is really important for information sharing, resource processing through specialized openings in the membranes and cell walls. So really, really important in those ways. And we'll begin today with another very strange property of water, which is the fact that water is at its most dense at 4 degrees Celsius, or about 40 degrees Fahrenheit. So a common property of just about every liquid and gas in general, and we've seen this a lot on this show, is that warmer gases and warmer liquids rise. They're less dense, and so they rise relative to the surrounding air. Air that is heated by the Earth's surface rises. That fuels convection cells that produces our weather. Water that's heated at the bottom of a pot rises to the surface, while cooler water sinks to the bottom. On the Earth, heated magma lava rises to the surface of the Earth to be let out, maybe by a volcano. On the sun, heated plasma in the sun rises to the surface. So in general, this is a pattern of both liquids and gases, that hotter liquids and gases rise, cooler liquids and gases sink. It's why your attic is usually warmer than your basement. It's why we can gaze at a mesmerizing lava lamp. So if we move this example outside, think of your favorite outdoor swimming spot. Hopefully the water doesn't look like this, but this would, or your favorite outdoor natural swimming spot. So like a lake, a quarry, a pond. Depending on how much mixing there is, you tend to have a thermal gradient in that water. Warmer water rises to the surface, cooler water sinks to the ground. So you're swimming in a lake in northern Wisconsin. The water feels good at the surface. You try to kind of keep your body flat, because if your toes get too far down, you feel that really cold layer beneath you. The water at the surface is not only being heated by the sun, which the water at the bottom of the lake isn't, it's also where warm water naturally accumulates the surface. So warm water at the surface If you dive down deep, you're going to experience the colder water beneath you. That's called the thermocline. And it makes sense because of what we know about cold water sinking, warm water rising. Eventually, that warmer layer of water at the surface, we're going into fall, we're going into winter, the lake starts to cool down, that warm layer gets thinner, it's not being heated as much, and the entire temperature of the lake starts to drop. As this continues, we start to get these hard frosts, the air temperature becomes really cold. You still have the warmer water on top, it's just relatively, you just don't notice it as much. You know, at some point the top of your lake might only be a degree or two warmer than the bottom of your lake, but you still have this gradient until the water reaches 4 degrees Celsius. Then something strange happens. That relationship goes away completely. It flip-flops because water is most dense at 4 degrees. So as water temperatures drop below 4 degrees, you get this situation where the water starts to expand as it cools. Usually liquids and gases expand as they heat. In this case, if you start going 4, 3, 2, 1, the water expands, becomes less dense, and it starts to rise instead of sinking. So the gradient starts to reverse. You no longer have cool water sinking, you have cool water rising. So maybe before you had 4 degree water on top, 5 degree water on the bottom, but now you reach a situation, you have 4 degree water on the bottom and the 3 degree water on top. And then eventually you get 2 degree water on top before the bottom, and then 1 degree, and then it starts to freeze. And then the first place to freeze, because the water is the least dense, is the top. And so this little fish here can swim around just fine under the surface, except now this fish, to get warmer, instead of going to the surface, is going to have to go down to the bottom to get to the warm water. And then the ice that forms also kind of creates this barrier between the bitter cold air and the water, and it starts to actually insulate. So that's, you know, water is one property we're going to talk about. It's very good at retaining heat, especially in a high volume. It's why it takes a pot of water so much longer to boil than a small one, a big one than a small one. And then it also means that the lake is going to take longer to cool down at this point. So even after several weeks of a really bitter Arctic blast temperatures, which Amanda, I promise you is not going to happen, you're only going to get about maybe a foot or two of surface actually freezing. So you have water freezing at the surface, less dense, and also expanding. And then that adds that other part is that water, as it freezes, so we already know that as it gets close to freezing, it becomes less dense, but as it freezes, it becomes even less dense. So again, in part 1, we talked about the water molecules are bonded together in these pyramidal structures, and the hydrogen bonds are flexible. So it's like they're being held together by bungee cords. They stretch, they compress, they break apart, they reform, and that allows water to kind of stay kind of small. But then when water starts to cool below 4 degrees and it freezes, that stretching and compressing starts to slow down, and the bonds become more rigid. If you think about it as you and your arms, like if you're warm, your arms, if you're a water molecule, your arms are flexible. And so if you wanted to if you're touching a wall, you could get close to that wall because your arm is flexible. You could kind of get tight. But if you got colder and your arms stopped being able to move, you couldn't get as close to that wall. It's the same thing with the water molecules. Those bonds become rigid, and then the space between them expands. You get more space within the water. And that's why ice floats so well. There's a lot of space in between there. It's much less dense. And as the water does this process and expands, it can cause tremendous pressure. Oh, here's an example of on the left, you have the warmer molecules that can get pretty close to each other, but then when it freezes, the structure becomes more rigid and you get fewer molecules in a given space. So then freezing water that expands, it can burst pipes in your home. It can cause a bottle. If you put a bottle in your freezer, it'll explode. It can even tear rocks apart. So as water, it can be tremendously powerful, as we know. And to complicate matters further, ice is not ice is not ice. Scientists have identified 17 different types of ice based on the temperature and pressure in which they form. So if there's little to no pressure beyond the ambient pressure, you get the lowest density ice. It's called ice 1. It's the ice you get from your freezer. There's no additional pressure. But if ice forms in clouds, where there's much lower pressure, it'll form a different structure. So if ice forms under pressure, the layers, so the layers, when ice freezes, it also forms these layers. And if it's under pressure, those layers will be closer together. So you can have ice of different densities that will, float better or worse. And again, this is all made possible because of those normally flexible hydrogen bonds becoming rigid. So we have ice forming in a freshwater lake at the top, because as temperatures lower, the water temperatures under 4 rise. But not all bodies of water are freshwater. We know that water is very good at dissolving salt. And when you add salt to water, it lowers the freezing point. It's why our cities put salt on roads, to keep water on the road milted for longer. They put salt on the roads, which then unfortunately runs into our streams and is terrible for aquatic life. And there are other more natural salts they could be using. I know once they experimented with beet juice. But the idea is you want to lower the freezing point of the water. So salt not only lowers the freezing point to below 0 Celsius, to below 32, it also gets rid of that whole system that we just talked about of water being densest at 4 degrees. So in salt water, cold water gets more dense all the way to the freezing point. It doesn't take that turnaround at 4 degrees. So in theory, the ocean wouldn't freeze the same way as a lake. In theory, the ocean would kind of continue that cycle of cold water sinking until the entire ocean is at the freezing point and then get the whole thing freezing. That doesn't happen for a lot of reasons, but one of the main reasons is that salt water itself in an ocean is layered in a different way besides temperature. It's also layered based on salinity. And so you have a salinity gradient in which the most saline water sinks to the bottom, regardless of temperature, and then the less saline water floats. So in the ocean, if it's relatively stable, and maybe the Arctic is the best example of this, you have a layer on the top of the ocean that's slightly less saline. It's the least saline of all the layers. And then, so even if that top layer gets cold, it's not going to sink, because the saline water, the more saline water below it stays more dense and it keeps the colder water on top, acts like a barrier. So less saline water always on top. And then once that layer reaches the freezing point, which could be about 28 degrees, that starts to freeze. And that's why you have ice forming at the top of the ocean. So both salt and freshwater bodies will freeze from the top, but for slightly different reasons. And then so with that, we'll kind of get into this, just like last week, a little lightning round of water facts, starting with a brain teaser. Does water make things more or less slippery? So if you tried to slide down a water slide and there wasn't any water, you'd probably have to do the butt scoot or the tummy scoot all the way down, because you might get friction, making that awful sound, between your bottom and the slide, and takes you a long time to get down. But if you add water to the slide, that water, even a little bit, acts as a lubricant, like a slippery layer. Right here. A slippery area between you and the slide. And you don't even need much water to go fast. There we go. If you had a lot of water, the current will carry you down. So then the friction isn't even a thing at that point. You're just going down a rushing water. But even a little bit of water will create a barrier enough that you have much less friction. And it's why water is such a crucial ingredient in one of my favorite childhood toys. So here we go. Water reduces friction and makes things more slippery. Right, but not so fast. when I'm at the Outpost on State Street and I'm buying my chicken, apologize, I'm getting some slow responses here. So I'm at the Outpost, I'm buying my chicken. I don't want that chicken to contaminate other things in my cart. So I like to put it in one of those compostable plastic bags, and I rip one off the roll, and then I spend 5 minutes literally trying to get this stupid thing open. That's what I used to do. Now that I'm older and much wiser, what I do is I walk over to the chest freezer, and the chest freezer has this ice crusted on the outside. And I just rub my fingers along that ice on top, which melts a small layer of water onto my fingertips, which provides just enough friction for me to finally get that bag open. So this is a case where water increases friction, but on the water slide, water was reducing friction. And that kind of conundrum can be explained when you look at the property of surface tension in water. So in the water slide, you have a high volume of water. There's a very low surface area to volume ratio. That water is very stable. There's also a lot of energy in the water caused by gravity. My body is is pretty big. So the surface tension is overshadowed by everything else, and water just acts as a lubricant. But in the plastic bag example, I have really tiny droplets of water on my fingers. And those tiny droplets have a very high surface area to volume ratio. They want to stay in that little tight formation, because just about any other formation is going to be really unstable. I'm also, my fingers are a little more delicate than a rushing water slide. So in this case, the surface tension is what kind of dominates the situation. And so in this case, the surface tension causes water to produce more friction in a time that I want it to. If we go back to the water moving down the slide, that water is traveling pretty fast. And one thing you learn, in physics is that when molecules move faster, they tend to produce heat. So then the question is, why, when water goes down a slide or moves fast, why does it not become warmer as it moves faster? And that answer can be explained in a couple ways. The short answer is that there are a lot of different ways that water molecules can move. So they can rotate, that's called rotational energy. They can vibrate, which is vibrational energy. They can also move from one place to another, and that's called translational energy. So rotating and vibrating water molecules is what increases water temperature. There's no net movement of molecules down a slide. All those molecules are just kind of bashing into each other in a pretty random way. And it's that tiny little bashing that turns their speed into heat, that speed energy into heat. And it can also be explained by the speed, because water molecules that are heated up in a stove or a microwave or something, those individual water molecules are moving at about 1,300 miles per hour, very, very, very fast. But in a tiny way and random and crashing into each other. Water in a fast moving stream, maybe 3 miles an hour. So it's for those two reasons. In a stream, the water is actually moving pretty slow relative, and it's all moving in the same way. So you have less of that, things bashing into each other. So that's primarily why fast moving water doesn't heat up the way vibrating or rotating water does. So if we look at a charged water molecule, so water molecules are charged, and when they're in the presence of an electric field, an electromagnetic field, any water molecules that are around will align themselves with that electrical field. So the positive side of water is going to, where the hydrogens are, is going to orient towards the negative part of the electrical field, and then the oxygen side is charged negatively, and that's going to orient itself to the positive. So if you put an electric field around water, you're going to get that water to orient based on that magnetic field. So now if you take a machine and you rapidly change the polarity, you rapidly flip the polarity with positive on the right and negative on the left, but then you switch them back and forth, with very high energy waves, let's call them microwaves, which they are. And then what you get is the water molecules are individually just going to go very fast back and forth between those pulsating fields, and they'll spin very, very, very fast. And then so obviously humans have taken advantage of that by creating a machine called the microwave. So essentially what your microwave is doing is it's producing this high frequency electromagnetic radiation field, and very constantly and quickly switching back and forth the polarity. So then the water molecules that are in your food begin to rotate very quickly and start to smash into the nearby food molecules, and then that energy is transferred from movement to heat, and that's why your food heats up. So this kind of leads us to the last big property of water that makes it so important in a way that we haven't mentioned yet, really, is that, again, it's good at absorbing and storing heat. We talked about that a little bit with the lake example. And like so many other strange properties of water, it's a result of those flexible hydrogen bonds. So for most liquids, if you add energy, that energy translates to heat pretty directly, movement and heat. And so for most liquids, it's pretty efficient. You add energy, it warms up. It equals faster moving, randomly moving molecules, and that means more heat. But when you add energy to water, the first thing to be affected is not the molecules themselves, but it's the hydrogen bonds between those molecules. So when you add energy to water at first, you're not moving the molecules around, you're breaking hydrogen bonds. That allows water to absorb a lot of extra energy before it even starts to heat up. But at some point, you kind of reach this tipping point where you've broken up about as many hydrogen bonds as you can. You've added a lot of energy to the system. Temperature still hasn't risen, but essentially you're going to reach a point where there's no more hydrogen bonds to break. And then the molecules start to absorb the extra energy, and then the temperatures start to rise. So this is why when you put a pot of water on, cold water on the stove, it seems to take forever for that temperature to rise. It goes through a really slow process of rising temperature. That's because that coil underneath that pot, the energy you're putting into it is not heating up the water very much at all. It's breaking the hydrogen bonds. But then when you kind of reach that tipping point, it's like when you're trying to put more things in a silverware drawer, right? You need to rearrange the silverware in the drawer before you can add more silverware, like your spatulas and things like that. So that's kind of what water is doing in that slow phase. It's rearranging, it's breaking the hydrogen bonds, it's getting ready. But then at some point, the extra energy then goes almost directly to heat. I guess it's kind of like when you take out a loan and your first payments are almost all interest, but then towards the end, it's almost all the other thing. And so then it takes a long time to get that water, up to this temperature, but then once it reaches this temperature, it starts to heat up much more rapidly. And the temperature that I'm talking about, where it's kind of that tipping point, is very important. So it takes a lot of energy to get that water up to a certain point, but then past that point, it takes very little. So then at the end, you can kind of hear the water, and then all of a sudden it just only takes a second for it to reach boiling. And so we'll get to that tipping point temperature in a minute here. Actually, we'll talk about it right now. So the tipping point water, where it's at its lowest heat capacity, is about 97 degrees. And 97 degrees is what we are roughly, right? We're a little 98, 97. So what this means is that our body, the temperature that our body keeps water at that point where it needs the least amount of energy to change its temperature. It's very easy and efficient to change the water temperature in our bodies. And that's important because if we get really cold, then it's not going to take a long time for our bodies to heat up. It's actually pretty easy to heat up our body temperatures back to where it was if it gets cold. Same if we're hot, if we have a fever, it's pretty easy to break that fever because water is at that point now where almost all of the input and output is direct. It's not, the hydrogen bonds. So almost all mammals and birds actually have a body temperature between about 85 and 104 degrees. So most of the warm-blooded life keeps their water in that temperature where it's easy to move up and down, which is pretty interesting. And then, another thing about water absorbing heat is that you get some, you get currents that will spread ocean temperatures across the globe. So you have, a current that runs up the east coast of North America to Europe that has a lot of water in it, but it's, it's not at that point where it's easy to cool and heat. It's that point where it's very stable, and additional, inputs are going to keep it at that. And so it's able to take the water, take the heat from the tropical areas and move it to places like Iceland and England and Sweden. It's able to really absorb and keep that temperature. And so ocean currents really kind of equalize you don't get the extremes that you would get between the coldest and warmest parts of the earth, because the water currents that can hold that water, because of that flexible hydrogen bonds, you get it kind of spreading. So that kind of puts the lid on the topic of water. It's everywhere. Life depends on it. We're made of it. It's deceptively simple, but unusual. It defies all the rules. It's tasteless, it's odorless, and it's a strange combination of weird properties provided mostly by that flexible, it's strong hydrogen bond that keeps us alive. And thanks again to the podcast, The Curious Case of Rutherford and Fry, who I pretty much used for these past two talks. But they asked the question, what is the heaviest animal that can walk on water? So is it a water strider? No. Is it a basilisk lizard? And I apologize, my computer's being a little slow. It's also not a basilisk lizard, and this slowness will give you a chance to guess what you think the heaviest animal is that can walk on water. And as soon as my computer is ready, it should pop it up. I'm sure you've got it in your brain. You're thinking about it. Suspense is killing me. There it is. You're seeing here, we got some elephants that are walking on water at the zoo. So thank you for joining me in this two-part series of water. I will stop sharing my screen.